Hopefully this week, if everything works out. Chemical equilibrium. It's the big deal. Couple pictures there. And I say they're not the best examples of equilibrium or non-equilibrium. I don't know, why might that be? Yeah, the equilibrium one is showing balanced. I say there's something wrong with it. Non-equilibrium, non-balanced. I say there's something wrong with it.
Equilibrium has to be equilibrium on both sides.
You're getting closer. Yeah. Forward and backward. The whole idea of this dynamic thing, right? That you have a forward reaction, reverse reaction. And someone was talking about rates. When the rates are the same for forward and reverse, then you're at equilibrium. So this stuff doesn't stop reacting. It's always reacting. Just the rates of forward and reverse are the same. Looking at these pictures, I don't see how this dude's going to go back, right? And then this one over here, I don't see any dynamic thing really going on there at all. It's not. It's a static picture. And that's not what you're supposed to think of when you think of equilibrium. It's not static. It's rate of change, but the change is the same going both ways. Okay. So, well, what could be an example? Finishing this thought, what could be an example of equilibrium then? Not chemicals. This macroscopic size stuff. What could be an example of equilibrium? A seesaw? I guess, right? As long as things stay the same. Yeah, because there's tension going back and forth. Yeah, that's kind of like a mechanical equilibrium, though, right? I think perhaps maybe the only thing that comes to my brain is, I don't think I did it with, I don't know if you remember your general chemistry class. I may not have done this demonstration with you, but you have a couple buckets of water. Give Mary Jane a big beaker and Joe John a little dinky beaker, right? And they sit there and they keep dumping, right? Sooner or later, they're transferring the same amounts back and forth, even though they have bigger beakers. One beaker's a lot bigger, so yeah, they end up having a lot more over there. But you can only transfer so much back and forth. So that's kind of a dynamic chemical equilibrium idea. Anyway, equilibrium constants. So if the rate of change going forward and going backward, if the rate of change is the same, that means the concentrations aren't changing. You can divide the amounts of products over reactants, and you should get a constant number. And that's what the equilibrium constant is. And hopefully see if you remember how to write an equilibrium constant expression. Before we do that, Erica, what was the symbol that we use for an equilibrium constant all the time? It's up there somewhere if you look at it. Big K. Big K was it. Right. And it was always what over what, Kimberly? It's always products over reactants, okay? And a little more specifically, Miranda, it was products and reactants, yeah, but what? Yeah, their concentrations, you're getting there, raised to their coefficients, right? Now, does anyone remember that? Ooh, here's brownie points. I gotta think of a better word than brownie points, right? That really dates me. What was the word for those coefficients? Starts with an S. Stoichiometric. Yeah, stoichiometric coefficients. So the concentrations of the products divided by the concentration of the reactants, everything's raised to the stoichiometric coefficients. So I guess you could write, how do you write concentrations mathematically, Pablo? What'd you write? Brackets, yep. brackets, big C, raised to the little c, brackets, big A, raised to the little a, big B. All right? Okay. How about units? Before we do that, well, maybe not. Let's just answer in the order we have. John, what are the units for equilibrium constants? Before you answer, the trick question. Kind of a trick question. It's a what? Louder. Be confident.
It doesn't have units.
It doesn't have units. They never do. They never have units. They never have units. None. The reason why, Adrian, is really the answer to this question. I don't know if you ever heard it stated this way, though. What did we always leave out of equilibrium constant expressions? We left out, well, it had to be pure liquids, though. Pure liquids. And what else did we leave out? Pure solids. You remember that? Oh, sorry, it's supposed to be down here. You're supposed to left pure liquids and pure solids. Right? This is supposed to be unitless. Pure liquids and pure solids. Why? They're there. Without them, you're going to be missing a reactant or a product that isn't going to work. Why? Why P-Chem people, Adrian? Adriana? I don't think we've got to it yet, though. Ooh. Right? Yeah, that's one way to think of it is that, I mean, if you have a pure liquid, its concentration can't change. And that's true, but the best argument is what Amanda said, standard states. Everything in a, well, I guess you should almost use the correct word. You probably shouldn't say equilibrium constant. You should say thermodynamic equilibrium constant. There's a big hint. Everything's dealing with energy. So, and if you take a look at, what do you got in here?
Water.
Thank goodness, right? Okay, you have water. Okay, how much energy does this water have? Right? Because it's like height. Okay, what's the height? You can use that for a lot of things. You can use energy of this water. You need to know it for some reason. How do you know? There's no absolute number. You have to measure it with respect to something else. You have to. You have to measure the energy with respect to something else. And that's what thermodynamics is all about. Energy. The natural way that things flow. Nature. So everything in that equilibrium constant expression, thermodynamic equilibrium constant, is with respect to, you don't see energy there. I don't see energy there, but it's going to be there. I just see concentration, but it's energy. Measured with respect to its standard state, everything. So these concentrations, with respect to their standard state, we never write it because we're too dang lazy to write it, right? We never write concentration of C all over its standard state raised to little c power. It's 1 molar. That's why we don't care. Because 1 molar is, raise 1 to what power, you don't care. It's gone. Pure solid. So everything has to be divided by their standard state. What are you measuring the energy with respect to? Well, with solutions, it's 1 molar. That's its standard state. Now, that might be coming up here somewhere. Oh, here, down here, of a solid, 1 molar. Now, if it was a gas, what do you have to have its standard state be?
1 bar.
It's 1 bar. Isn't that a funky thing? 1 bar. 1 bar. Right? Not atmospheres, a bar. A weird unit called a bar. And that's why this is important to understand. If you're going to use this equilibrium constant, you should say thermodynamic equilibrium constant, and there's a gas, and you have to put in its pressure, you're not going to put it in terms of concentration. They want it pressure for some reason. It better be in units of bar. Otherwise, you just plug, right? Your standard state isn't going to agree with the units you just used. So thermodynamic equilibrium constant, gases have to be in a bar. Okay. So the reason why pure solids and pure liquids don't show up is because what's the standard state of a pure solid? The solid, the pure solid. What's the standard state of a pure liquid? A pure liquid. So they cancel out. There's nothing to write. They cancel out. So that's why they're gone. And that's why you never see pure solids, pure liquids, because their standard state is a pure solid or pure liquid. All equilibrium constants are unitless because they're always with respect to their standard state. And what are the standard states? Well, we almost always write in terms of concentrations. It's almost always 1 molar. But sometimes you might have to worry about a bar. Or if it's a pure liquid, then the standard state's a pure liquid. But, yes?
So if it's an aqueous solution, it stays there, or is that the same as pure liquid?
Aqueous is solution. Yeah, there's a lot of words that mean the same thing. Aqueous means, aqueous, that's solution. Solute, that's referring to solution. Solution is solution. Is there another one? That's about it, right? I guess mixture, maybe.
So do you keep the aqueous of the...
Yeah, really nothing changes. Everything we've done in the past, we're still doing. Except now you just know a little bit more. You know why pure solids aren't there. You know why pure liquids aren't there. And if you ever have, instead of a brackets, and you have a P raised to its little power, I don't know, 3 or something, you better have it in what units? That gas, that pressure. Bars, right? But for them to be specific, they should be giving you the thermodynamic equilibrium constant. Then you know P has to be in bars. Otherwise, what the heck? I don't know. Right? So that's, but you know, people get, in books too, they get lazy with their terminology, so that's okay. We just have to live with it. That's the job security in it, I guess. Okay. Where are we? Manipulations with equilibrium constants. We flip this reaction. Just flip it. Make the products the reactants. Danielle, the reactants the products. What happens to the equilibrium constant expression? All right? No? What's going to happen? Does anyone see? If I flip the reaction, what's going to happen to that K expression that you're going to write? Yeah, it's going to be now it's 1 over, yeah, that's one way to say it, is what Nyla said. It'll be 1 over K. All right? You flip the reaction, that equilibrium constant's going to get flipped. Or just think of it this way. These guys are now on top. Those guys are now on bottom. Same thing. You just flip the equilibrium constant. Okay. That makes sense? How about this one? You have three reactions. Equilibrium constants K1, K2, and K3. Okay, they're all added together. So we have this reaction with a K1 equilibrium constant, a K2, and a K3. We add them all up. All right? What would K4 be? Yeah, now there's the question. How do you involve all these Ks to get the K4? Do you add them up? Now you definitely add up all the reactants and products to get this guy. Does anyone know? Oh, you can. If stuff is on this side, you can cancel stuff out. Yeah, that all works. You know what this number is? You know what that number is? You know what that number is? These equilibrium constants. You know that you added up all these three to get this one. There's a straightforward way to get K4. You want to prove it to yourself? You pretty much have to write all this out. You just end up multiplying them. You multiply K1 times K2 times K3, and you'll get K4. You almost have to prove it to do it to prove it to yourself. But you multiply the Ks. When you add up two reactions, what's the equilibrium constant of the final result? Just multiply. If you know the individual equilibrium constants, just multiply them together. Okay, so there might be some homework missing with that. a reaction is spontaneous, what does that mean in the world of thermodynamics? Nyla, what does that mean?
Is it like random?
I think it's spontaneous. Don't you think of this? That's spontaneous. Right? Psh, psh, it's spontaneous. Spontaneous. It's not really random. It just means that it's going to happen really, really fast. That's what you think of when you think of spontaneous. But that's not what they mean. That's when we're talking. But if thermodynamicist is talking, they use the word spontaneous. It could take a million years. A thermodynamicist correctly states something this way. I hate wearing rings, but I should be wearing it, right? My diamond ring, thermodynamicist and me saying this, my diamond ring will spontaneously turn into carbon. Nothing wrong with that statement. It's going to happen. It will happen. You can't stop it from happening. It's going to take a long time, but who cares? It's spontaneous. It's going to happen. Time has nothing to do with it. Okay? It just means that it's going to happen. That's all spontaneous means. Okay. So when we're doing this reaction spontaneity stuff, don't think that it means, oh, it's going to happen like that. It just means that it's going to happen. And some things are going to more likely to happen sooner than others, and that's kind of where we're getting at. Reaction spontaneity depends on 3 factors. And there's a hint. Jamesa, what are the 3 factors that determine spontaneity? Whether the reaction is going to actually proceed or not. Who cares about time? It'll just proceed or not.
Isn't it changing heat?
Okay, she says heat is one. She's on to something. If you have a reaction and it gives off a lot of heat or it sucks up a lot of heat, which one is going to be more natural, more spontaneous? And natural is a better word than spontaneous, I think. Gives off, right? Gives off, exothermic. That's the one where, yeah, things are much more spontaneous. So which one of those symbols up there is really giving off heat? Heat, the delta H. There's our heat. Okay. There's a couple more. Miriam? And the hints are supposed to be up here. Entropy. That's the delta S. Okay. You can kind of think of it, again, the books don't tell you the whole story, and they probably should tell you the whole story from the very beginning. I mean, you could take it. I really think you could. Entropy is not... I don't want to use that. But you know, if I took this, smash it up, make a big mess, try to spread stuff around, it's not entropy. Entropy is having something to have a whole bunch of different possible energy states. Instead of just one, give it a whole bunch of different possible energy states and different ways of organizing itself to get those different energy states. A whole bunch. That's all entropy is. And that's delta S. Okay. Then there's one more. Everybody's going to be temperature, big T. So do you want for it to be a spontaneous, for it to be a naturally occurring reaction, would you want T to be really, really big or really, really small? Really, really big. Why? Yeah, units, I guess it just depends on what delta S is in. You're right, but why really, really big? The hint to me is we said delta H was the heat. And we already know that's exothermic. It's what sign? Positive or negative? Negative. Negative heat's exothermic. So if you want this guy to be negative, exothermic, that means things are spontaneous when this delta G is getting to be really, really negative or really, really positive. Negative. That's spontaneity. That's when that delta G, what's the delta G called?
Gibbs.
Gibbs free energy. So So when the Gibbs free energy, the change in Gibbs free energy is really, really negative, man, we're talking something very natural. It's going to happen, definitely. It's going to happen right around the corner. Not necessarily, but odds are it will. So delta H, that's how you want to get all this stuff negative. And I think Jeff is right. It has to be Kelvin, because otherwise it's going to mess up our whole story here. Because can Kelvin ever be negative? No, it can't be negative. And you want things to be really high temperature, more natural, more spontaneous. So, yeah, it has to be Kelvin then. So the bigger the Kelvin, the more spontaneity. So delta G, answering that question, Natalie, delta G is what? 0 for spontaneous reactions. Less than. You want it negative. Exactly. Good deal. Okay. Let's see if you remember this, Jeff. How did we get numbers for this? How did we get numbers for that? You did it for maybe a week of your life, maybe even less than that, in general chemistry. How did we get numbers for those? We have some reaction, just like this guy up here. I could get a delta H and a delta S for him. How did I do it? Anyone remember? Tables. Tables. That was coming up? Nope. What we had to do is, if we had a reaction, I can remember, well, just stick to this guy. He's easier to see. What we have to do, find tables for delta H. Look up delta H for this product C. For all the products, actually. Add up all the delta H's for all the products. If it's a little stoichiometric coefficient of C out front, multiply the delta H for that product by little c, right? And then we added it up all the delta H's for the reactants, multiplied them by their stoichiometric coefficients, right? You remember? And then we subtracted products minus reactants. Whose law was that? Anna? Adriana? Hess. Hess's law. That was Hess's law, where he just did that. And technically, it's not delta H. They're going to put a little F on it. Enthalpy of formation. But that's delta H. Okay. Do the same thing for delta S. You just have to find not a delta H table, but a delta S table. That's all. And do the same thing. Products minus reactants. So you can get numbers for those. And you plug them into here. Right, whatever the temperature is of the reaction, and if it's negative, hey, it's going to be natural. It'll happen. Okay. Equilibrium constants and Gibbs free energy. Kathleen, the more spontaneous a reaction, then K is what? There's supposed to be a hint here in the equation. But maybe just thinking about it wise, you can answer it too. Smaller? Think of reactions as, K is always what over what? Products over reactants. I always think in terms of products. If, in my brain, I would reword this question. If K is really, really big, that means I have a whole lot of product. If K is really, really small, I don't have hardly any product. So I always just think in terms of products. So what sounds more natural? To have a whole lot of product or a little bit of product? Whole lot of product, right? So just by, guessing, I would say big K means that, yeah, it's probably this more spontaneous reaction than a smaller equilibrium constant. But the real answer is you're supposed to look at the math. What's this little thing? That's that, that little, what is it, 2 point? There's a number for E. It's everywhere in nature. Isn't it 2 points? Is it something? It's 2 point something. But you can find it on your calculator, but it's just that little E. It shows up everywhere in nature. You raise that number to negative delta G over RT. What's R? What's big R? Hint, PV equals nRT, gas constant, right? and T would be your temperature. What's this thing doing here?
Degrees.
It's not degrees. It means what? It means you use the tables. It means you use the tables. Because if you fix temperature and pressure, you can look up numbers for all this stuff. So if we use tables, life is so much easier. Right? If you don't have the little zeros in there, that means you can't use the tables. Okay. 25 degrees Celsius in 1 atmosphere. So that's all whether the little zero is there or not. It's the Gibbs free energy. And remember, it's supposed to be, for spontaneous, delta G is positive or negative. Negative. Negative times negative is a positive. So e to a really big number is going to give you a really big number. Le Chatelier's. Oh, we didn't finish all this. The more spontaneous a reaction, then delta G is cat. More negative. So what would be more natural or more spontaneous? Negative 100 or negative 10? Negative 100. It's just kind of you just have to get used to it. Le Chatelier's principle. Amanda, what is? I'm not even sure if I'm pronouncing this guy's name right. Le Chatelier, but what was that? Exactly. Everything about being balanced. This chemical equilibrium is supposed to be dynamic. You have a forward reaction, and its rate is the same as a reverse reaction, right? And then everything's nice and balanced. Well, you mess with it. You add some stress. And there's a lot of ways to add stress, and here's some listed right here. And then you see what the effect is. Let's play the game, see if this works. Since we're talking about dynamic equilibrium all the time, I should have a double arrow there. But if the above reaction is at equilibrium, will more or less of this bromate, BrO3 negative, exist at equilibrium for each case? Now this is really practical stuff because, I don't know, bromate could be some really, really expensive reactant. I don't know what you're trying to make, but something really expensive, some anti-tumor drug or something. And you're spending a lot of money for this stinking stuff. You want it all to react. So you mess with the equilibrium conditions, you mess with the little reaction vessel, you mess with everything you can to get as much of that stuff to react as possible. That's the game you're playing. And or it could be, or you could have a product, same story. You argue with trying to get the most of it. Okay, so we're at equilibrium. Will more or less bromate exist if we do the first thing? Number one, we are adding sodium bromide. No name. Someone just failed their quiz. Adriana. We're going to add sodium bromide to the mixture. Adriana, I'm picking on you. We're going to add sodium bromide solid. Would we end up with more or less bromate? What'd you guess? Now, first thing, shouldn't she be looking? I was hoping she would have said this. No effect. Well, no. Because there's water. See all the ions? So there has to be water there. There's some solvent. So even though they say solid, this stuff will dissolve because, that's something we should review. What's that one? The only solubility rule that I expect you to know. Anything. You okay? That's okay. Anything with this ion, with these ions, will completely 100% dissolve. That's the only solubility rule you need to know. And it'll really, 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 really help you. So when you see sodium bromide solid. Okay. But before I get on with that point, the point I was hoping Adriana was going to say is there isn't going to be any change because this is not up there, right? That's what I was hoping she was going to say. Because I don't see NABR up here anywhere. But then I'm supposed to say, Adriana, remember this? I should have planted the wrong answer. Okay, remember your solubility rule. You have this guy, this sodium bromide, is going to break up into what two ions? Na plus and Br minus. That's what you got to look for. So, okay, Adriana, now look up here. Oh, there she sees it. She found it. So what is the effect? Now they added too much of this. It was nice and happy. Reverse rate was the same as the forward rate. They were producing and reacting at the same amount per unit time. But now you messed it up, you added bromide. What's going to happen? You have too much. It's going to have to. You got to make some more of this stuff. You have to. You have no choice. So you're going to end up with more bromate. Right? You end up with more. Because you have too much of this bromide, you got to get rid of it. It's going to go that way. That means you're going to have less of this and less of that because it's got to go that way. Does that make sense? Because the question could have been, what's the effect on the pH? Oh, that would have been a better question. I should have done that. Right? Okay. But the pH would have, right? Hydrogen ion concentration would have gone down. So that means pH would have gone up. That's even a better question. Okay, how about this one? A small amount of sodium phosphate is added, which preferentially precipitates chromium. What would that be? Chromium 1 phosphate, I guess. Chromium 3. This guy shouldn't be there. That should be CrPO4. Because those 3s are going to end up canceling on you. Do you notice that? This phosphate's a 3, chromium's a 3. A small amount of sodium phosphate is added, which preferentially precipitates chromium 3 phosphate. So let's pick on it. Let's pick on urandi. What is the effect on bromate? So you add this stuff, you don't see it up there, but then you have to read the rest of the sentence, right? What would you guess? What's the effect on the bromate? What's that? Guessing less? So what ion or what compound up there is it influencing? The what? The Cr+3. All right, so it's right here. So that's the first thing you have to do. There's only one other thing you got to do. Is that amount of that compound, that ion, is it increasing or is it decreasing? Increasing? It's precipitating. Yeah, it's getting sucked out of there. So if it's getting sucked out of there, what's going to happen to the bromate? I hear less, I hear more. It's both. There's a couple ways to think about this. You can think about it mathematically, because whenever you do products over reactants and raise to their stoichiometric coefficients, you always got to get K. Always. So you can do it mathematically and answer the question. You can do it kind of visual-like. I don't have a lump on this side. I don't have too much. I don't have enough. I don't have enough. So the only way to get more is to make more. I have to. So if I'm going to make more chromium 3, well, I'm going to make more water, but I'm also going to make more bromate. Right? So I'm going to increase it. Does that make sense? The effect on the chromium-3 is, yeah, it's precipitated out, so we're sucking it out of there. We're removing it. Maybe think of a hole. We're leaving a hole. You got to fill it, if that helps. But you got to get that equilibrium constant back. You have to. The only way to get that equilibrium constant back is by making these reactants, by making them bigger. Because you just made the number smaller. You got to make it bigger to get that equilibrium constant number back, whatever it is. Now we are doing number 3. We're adding, Anna, we're adding 0.05 mils, a 1.25 molar sodium hydroxide. She says less. It's a 50-50 shot. But I bet you the quiz is going to say, explain why, right? Okay, so I don't see hydroxide up there anywhere. It's too easy. Those easy ones are gone, right? So it's got to be interacting with something. Erica, what is it interacting with? Water? I don't know. H pluses. H pluses, right? So I'd say there's very few reactions that they've got to be at the top of your head. This isn't one of them, knowing what's going to precipitate. But this is. Oh, I know what this will dissolve. Sodium acetate, sodium phosphate, doesn't matter, right? Those have to happen. Then I can think the only other one that's a big deal is this one. That's going to happen all the time. And it's a big deal because that's your pH equation, that's acid-base chemistry, that's everything right there. Okay. So so hydroxide's interacting with the H+. Okay. Knowing that, what's the effect on the bromate? Was Anna right? Less? The H+, it's going to disappear, or are we going to be producing it? We're reducing that, right? That H+ is disappearing. It's going away. This H+ is going away. So the effect on the bromate, you got to get that equilibrium constant back. You don't have, I know, this is what's weird, I think, is that we can like to think of it as H+. The thermodynamic equilibrium constant doesn't look at it that way. It just looks at products over reactants. You better divide the two, and you better give me this number. Otherwise, you're not in equilibrium. So it looks at this. Products is too low. So you need more product. Generate it. It doesn't know it's H+. It's just mathematical. It doesn't know. So you have to take this and generate that. Well, that means bromate's going to go down, like Anna said. It has to. So it's less bromate. That makes sense? No? Okay. Start with, here, what we added. First, you have to look at that and not see the Na. Pretty much, I think in every question in analytical, except for a few, whenever you see these group 1s, keep a blind eye at it. Don't even look at it. You have OH. So that means we're adding OH. The first thing you do is look and see if OH is up there. It's not. Okay. What is it going to interact with? No, 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 no. Yes. So it's going to react with that. It's going to take those away. So now you have to think of what sticks in your brain the best. It's going to either leave a hole. You got to fill it. That works. You can think of it as the equilibrium expression way, where I don't have enough product anymore. That number's too low to achieve equilibrium. I got to generate more. I have to make this one smaller and that one bigger. But either way you answer the question, this is going to disappear on you. It's going to go down. Okay. One more. 0.05 mils of, who knows what acid this is? It's in vinegar. Acetic acid. Okay. Kimberly, we're adding 0.05 mils of 1.25 molar acetic acid. What would it be influencing? I think so too, but in a very minor way. Is this, have we memorized the 6 strong acids yet? We have? Okay. Is this one of them? No. But it's still an acid, right? So it's not going to kick out a whole lot of those H pluses. But it will a little bit. You're just making the solution more acidic is all. It's not going to do anything, but it's going to make the solution a little more acidic. Well, if it makes it a little more acidic, now I've got too much product, maybe a little bit, but still a little too much product. Right? I got to get rid of it. All right? So think of it as I have too much product or not enough reactant, however you want to think of it. It's going to have to shift to the bromate and make a little bit more. Not a whole lot, but the point is you'd have more. More reactant, because right now by adding a weak acid, it's still an acid, it's still acidic. That means there has to be some H pluses, and there are, not a whole lot, but it's going to make the solution more acidic. So a little bit more bromate, not a whole lot. It's not a reactant. We're adding some product. Reaction quotients. Reaction quotients, and here's a question for reaction quotients. If you don't remember what the heck a reaction quotient was, look at the question. This is why we used reaction quotients. They give us K. Here's initial concentrations for that reaction that was listed above, right? For this thing. Okay, they gave us the equilibrium constant for it. Okay. And they say, is it at equilibrium? If not, which direction will it go? Do you remember how to do this? How did we do this? I didn't make a table. You might have made a table, though. I don't know. If that's how you did it. What was the game plan for this? What we did is we plugged in all these numbers into K. But we don't know if it's at equilibrium, so we erased K and we wrote a Q for reaction quotient. I don't know why they called it that, but they did. So we plug all these numbers into the reaction quotient expression, which really is just the equilibrium constant expression. It's the exact same thing, but we don't know if it's at equilibrium or not, so that's why we can't write big K. I guess we could have wrote K equals with a question mark on it, but it's not how they did it. They said, nope, you have to write the reaction quotient, products over reactants, right? So you'd have to find the hydrogen ion, raise it to the 8th power, right? Times the dichromate, times the bromide. Divide it by, what? Is he going to show up? Nope. Chromium 3 squared divided by bromate. Whatever you get, there's your possibilities. If you got 2 times 10 to the 11th, and only if you get 2 times 10 to the 11th, then it's at equilibrium. Okay, now here's where it's tricky though. What if Q was, just pretend. Let's say I get 1 times 10 to the 11th. In which direction would the reaction shift? My Q is too big or too small? So don't worry about times 10 to the 11th part. It's too small, right? This number is smaller than that number. So this is too small. Think in terms of products. I don't have enough product. Q's too small, I don't have enough product. It's got to shift towards the products. Okay, that's where it would shift to the products.
So Q is too big. When it shifts the reactant.
Yeah, so let's say Q is, you do all your math, and you get, I don't know, 6 times 10 to the 23rd or something. I don't know. Now Q is too big. You have too much product, because Q is the product of reactants. Q is too big. You have too much product, so it's got to shift to the reactants. All right, that's how I look at these things. Okay. So I don't know what the real answer is. But you could work it out. Okay. Write the expression of the equilibrium constant for each of the following reactions. And they want the pressure not with brackets, but instead as, well, if it's molecule X, then it's px. So, Miranda, what would you write? Oh, be careful though. The little s means solid. So its standard state is the pure solid, so it just cancels out. Even though we never write standard states. So what were you going to write up on top, in the numerator? Just a 1. Just write a 1 up there. Good. How about in the bottom, Pablo? In brackets?
Yeah, so with the 18 brackets and raised to the 3.
Raised to the 3rd. Keep going.
And brackets the PO4.
Oh, there is no gas in this question. What was that one we're going to get about? All right. Okay. Well, if there was a gas, you just write P, right? And a little subscript would be the compound. The formation of tetrafluoroethylene from its elements is highly exothermic. Okay. A mixture of fluorine, graphite, and tetrafluoroethylene is at equilibrium in a closed container. Will the reaction go to the right or left if fluorine is added? Oh, man. John? Fluorine is added. So we're going to have, right, there you see here's your fluorine. We're adding that one. So it's got to shift. Yeah, over there, right? Because now we have too much reactant. You got to get rid of it. Shift to products. We have the equilibrium constant is messed up. It's not going to. Your Q would be too small because reactant is too big, right? There's a lot of ways to think about it, but it's going to have to shift to the right. All right. To products. Rare bacteria eats tetrafluoroethylene and it makes Teflon. You add this bacteria, which direction would it shift? Adrian? All right. We're adding something that's removing tetrafluoroethylene. So it's going to shift to the left. Everybody agree? We have more or less. You have less product. You don't have enough product. So you have to make more. It's got to go to the right. All right? Yeah, you're adding something, but you're adding something that's removing product. So what did I say? It's got to shift to the right again. So in all these, the game plan is just identify what side is being messed with, and it doesn't really matter what compound, it just matters what side. And is it going to be too much or too little? Okay, so we're about out of time, but it's the same story. And there's a lot of questions here you can practice with if you want. But come by and I'll be glad to help you out.